All right, so let's get straight into this. So, Chapter 8, Operational Amplifiers. So, just in case you didn't see the previous video, we're going through the Practical Electronics for Inventors, 4th edition, which is by Paul Schurz and Simon Monk. All right, let's get back to Chapter 8. So, the reason why we're doing this is I'm studying the Instrumentation and Control, which is a second year electrical engineering module. And in that, I need to learn about operational amplifiers. Now, it shouldn't be that big of a deal, but it is because I haven't studied analog electronics, which I should have studied prior to this one. So I have to go a bit deeper. And yeah, if you're currently studying this module, you might be like, this guy's an absolute idiot. Well, I am. Apologies. All right. So the plan is for me to learn about operational amplifiers and using Notion, create a whole bunch of flashcard questions kind of thing. So, for example, like what's the max output as it relates to voltage out, and then you know that that's 85%. Max output voltage cannot be more than 85%. Cool. Okay. So let's get cracking. Operational amplifiers are incredibly useful high-performance differential amplifiers that can be employed in a number of amazing ways. A typical op-amp is an integrated device with a non-inverting input and inverting input. Yep. 2 DC power supply leads, an output terminal, and a few other specialized leads used for fine-tuning. Okay. We've got specialized leads here. All right. The positive and negative supply leads, as well as the fine-tuning leads, are often omitted from schematics. If you do not see any supply leads, assume that dual supply is being used. Okay. Note that we have labeled the supply voltages V plus and V minus, which is these two, as they're usually the same. Huh? They're usually the same. Okay. However, they do not need to be, as you will see when looking at a single op-amp in this chapter. Okay, fine. So by itself, an op-amp's operation is simple. Oh, you're telling me? I've been trying to understand it for about 2 hours now. An op-amp's operation is simple. If the voltage applied to the inverting terminal, V minus, is more positive than the voltage applied to the non-inverting terminal, which is V plus, the output saturates towards the negative supply voltage. If the inverting terminal is more positive, why does it go towards negative? If V minus is more positive, it goes to negative. Conversely, if V plus, meaning the non-inverting, is greater than the inverting, the output saturates towards the positive. I thought it was the opposite way around. Let's have a look here. I'm pretty sure it was the opposite way around. Okay. That's just crazy. Why is it not loading now? Okay. Alright, well, that's not loading. We'll just pretend that loaded. Okay. It saturates towards the positive supply voltage. I don't get that. Okay. If the voltage applied to the inverting terminal is more positive than the voltage applied to the non-inverting terminal, the output saturates towards the negative supply voltage. Shouldn't it be going down? Why is it going up? If it's more positive... oh, wait. Okay. So you got the plus and the minus here. What we're saying is that if this one is more positive, this bit here is more positive than this, then the output goes to the negative. Okay, let's take a look at what my lecturer put in her slides, because I'm fairly certain it was the opposite. Tutorials. Okay. All right. Okay. In itself, the operation of OpAmp it's literally exact. She's copy and pasted it from the book. Shoot me now. Shoot me now. Okay. Let's just confirm it's the same. In itself, the operation of amp is simple. If the voltage applied to the non-inverting terminal V minus is more positive than the voltage applied to the non-inverting terminal, then the output saturates with the negative supply. So this is what. Okay. If this is more positive than this, then the output goes towards negative. Is that what we're saying? If the output at V plus is more positive, then the output goes to positive. Why? Yeah, I don't get it. I don't get that. This is where like I have a battle in my head where I'm like, do I just skip it and pretend that that makes sense to me? Because this crazy thing is I could pass the whole entire module and get top grades without even understanding this. But just, what's with the jargon? I can't take it. I can't take the jargon. Okay. But we're saying that. Okay. Let's look at it in terms of this. So this is V plus and this is V minus. Right? Okay. We're saying if this is more positive, you got a higher voltage here than here. This is 6 volts, this is 0 volts. We're saying that the output is going to go negative. And if this is more positive, you got 6 volts here and 0 volts here, then the output is going to go positive. Is that what we're saying? Okay, so here's an example. All right. So we're saying we've got 0 volts. No, I'm still not getting it. V supply minus V out equal to, yeah, that's not making sense to me. I mean, I don't know what to do. I'm on holiday now, so I can't actually use the internet where I am. I'm in like a remote place. Operational amplifier. I'm just searching in my Dropbox to see if I have another book that talks about it. Okay, so this is my lecture. Operational amplifier. See, I don't know if she's basically saying to me, well, don't worry about it, because look, this is not enough information to understand what's going on. Am I being said, don't worry about how it works, it's fine? Or is it just am I just being dumb? Is this just a thing where it's like, well, you idiot, of course it goes positive, of course it goes negative. I don't get that at all. Alright, so this is useless to me. I'm looking for another book that talks about operational amplifiers. That's a quote. Operational amplifier abstraction. Chapter 15, mate. Chapter 15. Who does that in your second year? Ugh. Okay, let's go to chapter 15. I'm a grown up man, and very rarely do I feel like crying. But when studying electronics from a book that's full of jargon, I feel like crying. Okay, so okay, here's some stuff. So the OpAmp is a multi-stage 2-input differential amplifier that is designed to be an almost ideal control device, specifically a voltage-controlled voltage source. Okay. An abstract representation of the operation amplifier shown in figure 15.1 suggests it is a 4-port device. The 4 ports are input port and output port. pair of 2 power ports. Okay. Positive VS supply voltage. For example, 15 volts. Okay, we're giving examples. That's nice. Give me examples, please. I enjoy examples. So voltage supply, a supply voltage at the positive end of 15 volts is applied at the power plus port, and okay, so a minus supply voltage supply is applied at the minus supply voltage of minus 15 volts. Don't you get a 30 volt difference across that? No? Because if you had that at 0, you'd have 15 volts across the amp. But if you're doing minus 15, then you've got 30 volts across it. That's how I understand it. Is applied at the minus port, okay? An input voltage, the control, applied across the non-inverting and inverting input terminals at the op-amp is amplified by a large amount and appears at the output port. What? An input voltage, the control, applied across the non-inverting and inverting input terminals of the op-amp is amplified by a large amount and appears at the output port. In the operational amplifier abstraction, the input impedance across the input port is infinity. Okay. And the output impedance is 0. The gain or the factor by which the input voltage is amplified is also infinity. I mean, why even spend your life writing books on this? Like, if everybody's just going to use the exact same definitions, why even write a book? Just, okay, why don't I just use the book from 40 years ago? You're just going to write the exact same thing. Speak English, people, man. Okay, this chapter uses the op-amp to construct more complex circuits using its simple abstract model. Internally, the op-amp itself is a moderately complicated circuit, and its design is beyond the scope of this book. Briefly, it contains input stage, not unlike the differential amplifier. Okay. Typically, op-amps have a second stage similar to okay. I'm looking for the bit about saturation. Historical perspective. Device properties of the operation amplifier. Let's just Google saturation. Search saturation. 297 hits. Okay. Gonna be a while. Is this still about op amps? Page 866. Yeah. The saturation so clearly present is missing from blah, blah, blah. Okay. But this isn't really what I wanted. This is too deep. Alright, so I just spent about 5 minutes, 10 minutes off camera taking a look at some other books. And yeah, I mean, basically, there's clearly something that I don't understand, whether it's about voltage or I don't know. There's something that I don't understand where I can't get my head around it. And I've looked at a bunch of different books, and the definitions are all fairly similar to this, so it doesn't really make a difference as long as they're using the same words. And I get it, books have to be like politically correct, and that's why, to be honest with you, I don't get that much value from books as I do from YouTube, because on YouTube you watch a video and the guy just says, "Oh yeah, the voltage just goes that way," and then you always get some guy in the comment that's like, "Well, it doesn't go anywhere. Voltage doesn't go; it saturates." So I get why books have to write words like this, but it doesn't make any sense to me. Like, I want to learn what it is. I don't want like, I'm not reading academic report or anyways, it's frustrating. So I've decided I'm just gonna skip ahead and just keep going, and hopefully either A, this is a whole bunch of boo-hoggy and I don't actually need to learn it, or B, I hope eventually I'll start to understand this. But yeah, I mean, if you can translate that into English words, please do. Cool. Okay. So at first glance, it may appear that an op-amp is not very impressive device. It switches from one maximum output state to another whenever there's a voltage difference between its inputs. Big deal, right? By itself, it does indeed have limited applications. The trick to making op-amps useful devices involves applying what is called negative feedback. Okay, so we're moving on to negative feedback. All right. When voltage is fed, I like that. Like, yes, please talk like this. This was going to make me understand things. When voltage is fed back from the output terminal, okay, to the inverting terminal. So what's this V minus? Okay, why V plus is down here now and it's grounded? All right. Okay. So to the inverting terminal, this is referred to as negative feedback. All right. What is negative feedback? When voltage is fed back from the output terminal to the inverting terminal. Okay, I'm okay with that. The gain of an op amp can be controlled. So the gain just means how much the voltage multiplied by, right? Okay. So the gain of the op amp can be controlled. The op amp's output is prevented from saturating. The op amp's output is prevented from saturating. The op amp's output prevented from saturating. Why? I don't get it. If you've got a supply voltage of 15 volts, how can it be prevented from going to 15 volts? Unless you're talking. No. I mean, surely the max is still 85%. Why would it? Oh, okay. So what you're saying is that it goes up linearly for a bit and then goes back into the negative feedback and then goes up linearly and it goes back into negative feedback. But okay. I mean, yeah. All right. Fine. Let's just basically at this stage I just kind of need to just accept that this is the truth. This is just all right. Cool. Take your word for it, mate. Love it. All right. So, for example, a feedback resistor RF. Okay, resistor feedback. That's fine. Nice name. Placed between the output and the inverting input, as shown in Figure 8.3, acts to convey the state of the output back to the op amp's input. It acts to convey the state. Mate, you know, I born and raised in London, speaking English my whole life, and I'm reading an English book that doesn't make sense to me. I may as well be in a foreign language. Okay. So, for example, a feedback resistor placed between the output and the inverting input, as shown in Figure 8.3. So, where's 8.3? This, right? Yeah. Okay. It acts to convey the state. It acts to convey, meaning that it's telling the state of the output back to the op amp's input. Okay. Okay. How is negative feedback done in an amp? I don't feel like I'll need to do this one, but just to make myself feel like I'm doing some work. The feedback resistor placed between the output and input terminal. I'm not going to say act convey because what does that mean? Placed between. The feedback resistor RF placed between the output and input. Acts to convey, sends the state of the output. So can just put sends the output back to your op-amp's in. Yeah. Okay. Fine. This feedback information basically tells the op-amp to read just. Oh, readjust. Oh man. Okay. To readjust. Is that how you write readjust? Is it not RE dash ADJUST? Okay, so this feedback information basically tells the op-amp to readjust its output voltage to a value determined by the resistance of the feedback. To a value determined by the resistance of the feedback resistor. How is it managing that? What feedback resistor? How does... Okay, so you've got 10 volts here at this point. Then how does this resistor determine what voltage ends up here? Okay, so you had 10 volts here, got 10 volts here. Then, okay, so you have a voltage. Oh, okay. Is working as a voltage divider. So if I had 5k ohms here and I had 5k ohms at the rest of this circuit, then my voltage would be split. Right? I think. Okay, so the feedback information basically tells the op-amp to readjust its output voltage to a value determined by the resistance of the feedback resistor. So the feedback resistor readjusts the output voltage. What does the feedback resistor... So it tells the op-amp to readjust the output voltage to a value. So that. As you can see, I'm super struggling with this module. Okay, so the circuit in figure 8.3 that diagram there is called an inverting amplifier. Okay. So let's just put here. Describe an inverting amplifier. Alright. Put that there, and then what I've got to do is just grab that. The hell, man? What is it? Alright, come on. Screenshot. What is going on with Notion today, man? Goodness sakes. So, alright, it has an output equal to minus V in... What does that mean? Is that the inverting? Times the feedback resistor over the input resistor. Because I'll learn how to derive this formula later on in the chapter. The negative sign means that the output is inverted relative to the input. The negative sign means the output is inverted relative to the input. The gain is then simply the output voltage divided by the input voltage. The negative sign means that the output is inverted relative to the input. The gain is then simply the output voltage divided by the input voltage. I'm reading that, it's not making sense to me. The negative sign means that the output is inverted relative to the input. Meaning just inverted from the input, basically. Or what does it mean by relative to it? Basically, so the output is opposite to the input, okay? If the input was 10 volts, the output is 1/10 of a volt. Right, different one. Okay, so the gain is then simply the output voltage divided by the input voltage. Output voltage divided by the input voltage. Okay, is that what they mean by inverted? The output voltage is divided by the input voltage. Or the feedback resistor divided by the input resistor. Okay, the negative sign indicates that the output is inverted relative to the input. As you can see from this equation, if you increase the resistance of the feedback resistor, there is an increase in voltage gain. On the other hand, if you increase the resistance of the feedback resistor, there's an increase in voltage gain. Okay. What happens when you increase the resistance of the feedback resistor? What happens when you increase the resistance of the feedback resistor? If you increase your resistance of the feedback resistor, there's an increase in voltage gain. Okay, and then the same when you decrease. When you decrease the resistance of the feedback resistor, then there is going to be feedback resistor. There's a decrease in voltage gain. All right, there's a decrease in the voltage gain. This is one of those where I'm not able to understand right now why that happens, but I get it, so I just accept it. By adding other components to the negative feedback circuit, an op-amp can be made to do a number of interesting things besides pure amplification. Other interesting op-amp circuits include voltage regulator circuits, current to voltage converters, voltage to current converters, oscillator circuits, mathematical circuits, adders, subtractors, multipliers, differentiators, integrators, waveform generators, active filter circuits, active rectifiers. Okay. Basically, don't know what any of these are. Alright. So besides negative feedback, there's positive feedback, where the output is linked through a network to the non-inverting input. Positive feedback has the opposite effect as negative feedback. Okay. Positive feedback. And what is positive feedback? But for now, I think my plan would be, although I don't understand what any of this is, I'm just gonna try and memorize it, and then hopefully, as I build up my knowledge of what's going on in this whole electronics world, then hopefully what I've memorized should come into play and sort me out. The positive feedback, has the opposite effects than negative feedback. It drives an op-amp harder towards saturation. Okay, where's the explanation of positive feedback? The output is linked through a network to the non-invert. Okay, so the output is linked through a network to a non-inverting input. Okay, positive feedback has the opposite effect as negative feedback. What effect does positive feedback have? So it's the opposite effect to negative. It drives the op-amp harder towards saturation. So negative feedback stops the op-amp from getting saturated, and positive feedback drives it towards saturation. So imagine, like, I could do YouTube videos where I talk about this stuff and it just sounds like I know what I'm talking about, because I can just say that and it's gonna sound good. But yeah, if I actually had to teach it, when you teach, that's how you know if you know something. And I guarantee you, most of our lecturers, if they went to a primary school and had to teach their topics, they'd fail. There's no way they'd be able to do it, because when you're dealing with primary school kids, they just say why. Well, why does it do that? What's the reason for this? And then they're just going to be lost. So, yeah. Okay. Although positive feedback is seldom used, it finds applications in special comparator circuits that are often in oscilloscope circuits. Positive feedback also will be discussed in detail in this chapter. Okay. Operation amplifier water analogy. I like water analogies. That's how I understand electricity. So this is the closest thing we can come up with in terms of water analogy for an op-amp. To make the analogy work, you have to pretend that water pressure is analogous to voltage, and water flow is analogous to current. So water pressure is voltage and water flow is current. I mean, that's how I see it anyway, so that's fine. I can pretend that all day long. The inverting and non-inverting terminals. This might be what I've been looking for. I hope it is. I love a water analogy. Come on. All right, so the inverting and non-inverting terminals of the water op-amp are represented by the two tubes with elastic balloon ends. These, right? Non-inverting and inverting. Okay, they got a balloon elastic ends. When the water pressure applied to both input tubes is equal, so both of these, the water pressure in both of these is equal, the lever arm is centered. Got it. Yep, that makes sense. However, if the water pressure applied to the non-inverting tube is made larger, so non-inverting tube is larger, it pushes it down, right? And forces the lever arm downwards. The lever arm then rotates the rotator valve counterclockwise, thus opening a canal from the compressor tube. Okay, so wait, how are we opening a canal? Okay, you got a compressor here. Here. Okay. Oh yeah, because the compressor is counted as the voltage supply. All right, I'm alright with that. Okay. The lever arm then rotates the rotator valve counterclockwise, thus opening a canal from the compressor tube, analogous to the positive supply voltage, to the output tube. This is analogous. What's how do you say that word? Analogous. And can you say it out loud? Not redacted, is it? Redact? Oh, whoops. Okay, wait. No, not that. Anyways, okay. This is an analogous. It's an analogy, right? But I just said it, I don't know. This is analogous to an op-amp saturating in a positive direction. Okay, what we're talking about here. You're putting pressure on the non-inverting terminal, and it's turning the lever arm upwards and opening the canal. Okay, so this bit here is going to remain closed because it's going to turn over to here, and it's still going to be closed here. But this bit here is going to turn to open here, and then now you're going to get water flowing here. So then this in theory has gone high. So the non-inverting terminal, the positive, has gone bigger, and then the voltage here has gone up to high. So if this one went bigger, the lever would go up this way, then that would open, and then it would, this output here would be low. I'm actually quite okay with that. Okay, so where was I? This is analogous to the op-amp saturating in the positive direction whenever the non-inverting input is more positive in voltage. Whenever the non-inverting input, non-inverting being the plus sign, okay, is more positive in voltage. So when it's bigger than the inverting input, when it's bigger than the lever, when it's bigger here, then the lever goes down and it goes. Okay, so wait, when the non-inverting is bigger, the voltage goes high. Is that what we're saying? Is that what it says here? So if the voltage applied to the inverting terminal V minus, right? So we're talking about here now, the bottom one, the inverting terminal. If that is larger, then the output is going to be low. It's more positive than the voltage applied to the non-inverting terminal V plus. Then the output saturates towards a negative supply. Yes, 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 yes. Okay. Okay. Oh, mate, I am happy. I get it. I actually get it. Oh, man. Screenshot this whole thing. Nice. Okay. Now, if the pressure applied at the non-inverting tube becomes less, non-inverting, okay, non-inverting becomes less, where am I? Less than the pressure applied. Okay. Less than the pressure applied at the inverting tube, right? So the non-inverting becomes less. That means that the inverting tube pushes higher, which rotates it that way, which means that it's going to go to the negative supply. Okay. The lever arm is pushed upwards by the inverting balloon. This causes the rotative valve to rotate clockwise, thus opening a canal from the vacuum tube analogous to negative supply voltage to the output. This is analogous to the op-amp saturating in a negative direction whenever the inverting input is made more positive in voltage than the non-inverting input. See what you can do with analogy in terms of explaining negative feedback. That is amazing. You know what? I respect you a lot, man. I love water analogies. It's just yeah, I love it. Absolutely love it, and I get the whole. It's not how electricity actually works, though. I get it. But I'm a year into this, man. Give me a break. All right, so where am I now? Okay. Also note that in the analogy there is an infinite input water impedance. Thank you for bringing this into it because I didn't get it as well. So okay. In the analogy, there's an infinite input water impedance. So we're saying that we're pumping water into these two inputs here, and there's no resistance to the water reaching the balloon. The water just gets there, right? So you can imagine, like, for example, if this terminal had a whole bunch of gunk in the pipe and the water wasn't getting there properly versus this one, then they wouldn't be balanced, even though the voltages would be balanced. I get it. So there's okay, at the input tubes, while there is zero output water impedance. So this is the output. There's zero output water impedance. So if it turns this way, the water just flows out. Okay, wait. No, I didn't get that. I've misunderstood it. So you've got infinite here impedance. Oh, does that mean that the water's not going anywhere because obviously it's hitting a balloon? Yeah, that would be crazy, right? Because if you didn't, let's say the balloon had a hole and it was just pumping water out, then obviously you'd have zero impedance. The water is just flowing out. But you've got an infinite impedance because the water can't go anywhere. The water is completely stuck there at infinite impedance. Just like if a 6'5" big guy stood in front of you, you've now got infinite resistance. You ain't going anywhere. Yeah, okay. This is infinite resistance, infinite impedance, basically. So the word impedance is confusing me. I understand resistance. I haven't done inductors and capacitors yet, so I don't understand impedance. But yeah, just in my head, resistance, impedance, cool. But this has infinite impedance because the water is not going anywhere. It's just moving a lever arm, but the water's stuck in the balloon. And this output bit, the water's flowing like crazy, completely free, with no one blocking it from anywhere. Therefore, it has zero impedance. Again, I'm okay with that. As you'll see, ideal op amps also have similar input and output impedance. In real op amps, there are always some leakage currents. But hang on. As you'll see, ideal op amps have similar input and output impedances. Why are they similar? Ideal op amps also have similar input and output impedance. Okay, I don't get that. Alright, fine. In real op amps, there's always some leakage currents. Yeah, of course, that's fine. Alright, guys, I'm very happy and I don't want to carry on and end up confused again. But I'm very, very happy with that. Like, that is absolute genius. Shout out to the authors. Let me bookmark. Can I bookmark this page? I don't know if I can. Let me just highlight this whole thing. Actually, I'll tell you what I'm gonna do. I'm gonna copy, screen grab it all. Yeah, man. Shout out to the authors. I forgot their names. I'll go back and get it for you now. Let me just save this. So I have it. Okay. All right. So yeah, man. Page 637. Let's get the author's name. Shout out to Paul Schurz and Simon Monk. I mean, I was stuck mate, I was fully ready to give up. I was just gonna basically say to you guys, look, there's no way I'm gonna be able to do this, so I'm just gonna have to just go back and study digital electronics again and then analog electronics again. But the fact that they've done that, I get that. I understand. It makes sense. Get it. I don't get how it works on a transistor level, but that's fine. I don't need to right now, though. I do need to learn that eventually. But for this module, I just need to understand what it means that the non-inverting terminal is causing the output to go towards the positive supply, and the inverting terminal, if there's more voltage there, I was about to say pressure there, there's more voltage in the inverting terminal, then the output is going to go to the negative supply. Sorted. I'm done. That's cool. I'm completely okay with that. Thick. Absolutely. I'm ecstatic. That is good. Really good. All right, guys. I don't know what I'm going to do in the next video. Probably continue on with this book. So, yeah, if you enjoyed these videos, give a like, subscribe, maybe send to your friends and say, look, there's this idiot on YouTube that doesn't know how to do anything. It's quite funny to watch and maybe we might learn something. So, send it to your friends as well and tell them to subscribe. Thanks, guys. I appreciate you watching. See you guys in the next one. Peace.